So, good afternoon, ladies and gentlemen. I'm going to replicate the talk we've just seen, replacing weird machines with universal composability. So, if you care to come up and give me your slides. So, this work is something that I've been caring for with Riyad, who is a student at Stanford, and Robert, who is a senior researcher at CISPA. And the overall goal of the work that we want to do is to unveil this similarity between these two very seemingly different fields and understand how each of these fields can explore from the benefits of what is being done in the other fields. And though for those of you that know me, the real nice thing of doing this work is that we can use 4 colors. And the point is that we have 2 systems at hand. Each of the 2 systems is composed of 2 parts. We have secure compilation, where, as we've seen, we have source languages and target languages. And we have universal composability, where we have, on the bottom, the protocols that are done in the so-called concrete world, or real world. And then the ideal functionalities, which are done in the ideal or abstract world. And so now, I will go into the details of UC first, and tell you what secure compilation is afterwards, and wrap up with what the analogy is and what are the benefits that we want to read from this. Now, apologies to the cryptographers in the room, but I'm not a cryptographer yet. And so this is my understanding of UC. So UC is the gold standard for proving that cryptographic protocols are secure. And the reason that UC is so good is that oftentimes cryptographic primitives are proven secure in isolation. And then when these are composed into larger protocols, then something in the protocol breaks those security guarantees that were proven in isolation. The good thing about UC is that by proving that a protocol is in UC under this concurrent compilation, these cryptographic guarantees are, the security of these cryptographic guarantees are guaranteed to hold no matter what other sub-protocols they are composed with. So we don't get exploits by composing subparts of the system together. And UC was developed quite a while ago, in the early 2000s, and there is a 5th revision going on, fixing bugs that have been discovered through the years. And there are alternatives that have been recently proposed, specifically the super amazing universal composability framework and the interactive UC framework. And for what I will describe now, I'll describe a general flavor of UC, though I will lean towards these newer theories for universal composability. And I'll tell you a bit more about SOSI and IUC later on. Now, the key notion about, in order to understand universal composability, is that everything is an interactive Turing machine, and interactive Turing machines are Turing machines that supposedly operate concurrently, but really they operate under a sort of sequential memory. So there's only one that is active at a time. The main thing that cryptographers like to define is protocols, and they are done using concrete crypto. And for example, if like this is an example from the existing literature, and this is for a commitment protocol, and it says that when you receive a commitment for a bit 0 or 1, then you compute some group element. So in this case, they go into the details of the actual crypto that they're going to use. So this is going to be probably some elliptic curve crypto. And then they send a message, com SIDY to the receiver after doing their cryptographic business. And then upon receiving com SIDY, then they output a received message. So this kind of describes the protocol for the commitment. And at some point, they abstract this behavior away. So this is perhaps a bit messy to completely reason about, right? And then they say, well, this protocol really, what this does is in an abstract notions is, well, upon receiving a commit SID message, then it records the value B, which is the bit upon which you're committing, and then it sends the message received back, which is exactly like this message here. So these are the main 2 elements that cryptographers define when defining UC protocols. But then in order to prove that their protocol is UC, they need to embed these elements into a bigger soup, if you will. They need to consider attackers, and they have attackers operating at both levels of abstraction. They have concrete attackers and simulated attackers, so attackers at the ideal functionality level. Finally, the last ingredient that we need in order to understand UC is that all the interaction that is going on between the protocol and the attacker, or the ideal functionality and the simulator, so which is the ideal attacker, is witnessed by an environment Z, which is objective. It doesn't mess up with the parties. It just witnesses what's been going on and observes the pattern of communication between the attacker and the protocol. So if we like diagrams, and apparently we do very much, we can draw UC sort of like this. And if we say that a protocol pi is universally realized by a functionality f, if no matter what attacker A it interacts, it is composed with, there exists an ideal simulator S that is composed with the ideal functionality, such that the objective witness, the environment, cannot tell up to some probability, which is why we have the squiggly signs, up to some probability, the environment cannot tell whether it is witnessing the interaction at the concrete world, or whether it's witnessing the interaction in the ideal world. And if we throw out all the quantifiers, we see, well, target attackers are universally quantified and generally poly-bound. Doesn't need to be, poly time is some security parameter because it's descriptive. Then the ideal attacker is existentially quantified, and the environment is also universally quantified. Now, UC is great. It lets you modularize protocols and reason about them using small building blocks, which makes sure that if you're proving that a small part of your protocol is UC, then you can reuse that same proof and that bit of the protocol in a different, larger protocol. So this seems intuitively the way to go for proving security of crypto protocols. Fortunately, for people that are doing research, there are also still some issues here and there with UC. The formalism is in which UC protocols and ideal functionalities are defined is a bit informal at times. Oftentimes the protocols are given in pseudocode definitions. From a PL perspective, proofs are fairly informal and mostly textual, and there is practically no mechanization of UC results, save for one very recent result that I can talk about more later. Now, there is existing work. I mentioned these alternatives to the UC definition, this SOCI and IUC, that do amazing work in addressing some of these issues. Specifically, they define more rigorous, more formal formalizations for protocols and ideal functionalities. They give semantics to these, but at the same time, they don't address points 3 and 4. And this is what we hope that our analogy can help. So we believe that the work of ours can help UC into addressing points 3 and 4. On the other hand, we also want to steal something from this community, and what we'd like to gain is some more reasoning about compositionality, as we have just seen, right? Because the big plus of having proven UC is that if you have that the protocol pi1 is UC realized by a functionality f1, and you embed pi1 in a bigger protocol, and you embed f1 in a bigger ideal functionality where the common part is written in the same form, in this pi bar, then we gain for free that, this we can do because they are all interactive Turing machines. So despite the fact that they have colored them differently, they can talk with each other freely, because they are roughly in the same language. And what we get for free from the UC composability theorem is that the bigger protocol UC realizes the bigger ideal functionality. And if we extend the definitions, we see that this is simply because we have added the same part of protocol on both sides, and we've isolated the pi1 and f1 on both sides and proven the subpart to be UC. So hopefully we want to reason about this compositionality for secure compilers as well. Now, this is as much as I know about UC. And let's dive into what I want to consider as secure compilation for this talk.
Sorry, can I ask a clarification?
By all means.
So you get to see all the, sorry, not the adversary, the environment. Does it get to see all the interaction between the adversary and the protocol, or are there specific things that are categorically given to the environment?
I think, off the top of my head, I can't remember. So normally, I think wherever there is often I recall seeing often that when there is a communication between the attacker and the protocol, there is often a message sent in the environment as well, so the environment is notified of that. I remember, or at least I remember seeing it in some protocols. I don't know if that is done on all protocols. If there is someone that has worked on UC more than myself in the audience, please,
It's explicit.
What?
It's explicit.
It's explicit, right? It can be different, right?
Okay. I don't recall it clearly. I've seen it done.
But it usually just makes the correct.
What?
So you usually will be the explicit thing, right? I think in general it's usually what you're saying. It's just kind of.
Or you recall the interaction in most cases?
Yeah.
Okay.
Okay. So let me tell you then what we consider for secure compilation here. We have a bunch of options to consider. There's fully abstract compilation as being the standard for the last 20 years. We have defined some alternatives more recently with Deepak. Katalin and his group has defined some. None of this, we believe, is what fits the picture. What fits the picture is this, which you've seen in other colors. What fits the picture is picking a criterion from our recent work from CSAP last year about journey beyond full abstraction. And as you already know, all of the points in this diagram correspond to a criterion for a compiler preserving a specific class of properties or hyperproperties. And what we're interested in is that bit over there, which is robust hyperproperty preservation. So the criterion that tells you that a compiler preserves arbitrary hyperproperties robustly across compilation. Now, RHC, this criterion, is we can draw it as follows. We can say that for any attacker that our compiled program is linked against, any trace which witnesses the observable behavior that is produced by that linking is also replicable at the source level by a source attacker operating with a source program. And what I write with bow tie here is just the normal linking, plugging of a context hole with the program. I just write it with a bow tie because I'll need to draw a visual analogy later on. But this is just, these attackers are arbitrary program contexts, and the compiled program and the source program just fill their hole. And if we state there the formal definition of RHC, we say that of any compiler's RHC, for any program, for any target attacker, there exists a source attacker that for any trace this holds. And with this diagram in hand, then we can put them side by side and try to see the analogy that we're drawing forward is a bit clearer. There are some slight differences here and there, which are open for debate, but concretely, we can see that each element of UC has a correspondence in RHC and almost vice versa. So we have our protocol, which is our compiled program. We have a universally quantified concrete attacker, which is our universally quantified target level attacker. The ideal functionality is the source program. The existentially quantified source attacker is the existentially quantified source level context. And then this objective witness, the environment in UC, is, well, the semantics with and the traces that are produced by the semantics. So when we spell out this analogy, we see that indeed not all elements of one world exist in the other. For example, while we have compilers that indeed take our high-level, human readable and human codable programs and turns them into bytecode and messier low-level languages, what happens in UC is that generally there is a human translation between a protocol and the native functionality. So cryptographers still think in terms, if you want to, the POPL analogy that I have in mind is that cryptographers often write assembly and then they try to derive their Rust code from it, right? A more high level and neater abstract representation of what they actually wrote. On the other side, well, you see they have this amazing general composition result, and we don't have anything like that in robust compilation yet, and we've seen that apparently this problem of we don't have a composition result is apparent for any analogy you try to take, when you try to bridge secure compilation with other theories as well. So our claim is because of these many analogies, we hope that development, meta-theoretical developments in one world can be borrowed in the other and vice versa. Specifically, the benefit that we foresee for once we concretize this analogy is that if cryptographers start to take the secure compilation approach to proving UC, it means that they have to specify protocols and ideal functionalities as programs, so with formal semantics, which in turn means that things cannot be hidden away in natural or tag language or pseudocode, but they need to be explicitly made. All these little hidden assumptions that hide here and there in protocols. They can gain access to more formal UC proofs, and the goal that, one of the points that we made for doing that work about the criteria are more amenable to mechanization than what the previous criteria were. And so we believe that by adopting these, then hopefully you can actually gain mechanization of UC results in an easier way than what is currently done. And on the other hand, we hope that indeed we can use these UC results to understand better how to compose secure compilation results. And there might be more. I can say I have explored all possible benefits here, and this, as you can tell from this talk, we're still rather early in this stage. So if you have comments, feedback, and interest, please come talk to us. So the roadmap we have for the future is, on the UC side, we want to formalize functionality and protocol in the ISC, which is this interactive lambda calculus that the SOSI framework does, and which is basically a way to give formal specification and formal semantics to protocols and their functionalities, and prove that the compiler there is RHC, which in turn would give us that those protocols are UC realized. And then on the other side, we need to formally prove that some version of UC, and we are looking at this IUC and RHC are equivalent, so we want to formally state this analogy. And because, as you've seen, there are many other points in the lattice, there are other criteria, and so we want to make sure that there is actually no better choice. We could have instantiated this analogy with something else rather than RHC. What tells us that RHC is actually the right choice? So we hope to do that properly. And for the secure compilation roadmap, when I taught about RHC, I was talking about the compiler, and I mentioned, well, mostly just referring to the language translation phase, but fortunately, in the paper, we are very explicit about not just mentioning compiler, but touch all other elements that are in a real compiler, for example, linkers. And if we assume that we have an RHC compiler from source to target, from another language to a target, and from a target to a bottom language, what can we say about the compiler that goes from the source to the bottom through the target language? What can we say about the compiler that takes input from both languages and links them together? And what can we say about the program that is obtained, the target level program, that is obtained by linking together two securely compiled submodules, right? And so these, I believe, are rather interesting questions that we hope to provide an answer to at some point. Before I conclude, let me take the first question, which is, but fully abstract compilation is what we've learned to love throughout many years. Isn't UC fully abstract compilation? No. And my reasoning for that is that full after compilation is relational, so we have two programs, but we have two programs in the target, and we have two programs in the source. And when we try to draw the analogy with UC, we don't have a second protocol, and we don't have a second ideal functionality. So if you try to connect each of these elements to something on the left, well, P2 compiled and P2 not compiled, they don't have anything to correspond to. And I was informed, how much time is it? Okay, fair enough. There is another analogy, but fair enough. So the bigger point, and now you bring out the guns. So the bigger point that I think is true is that full after compilation, when we talk about secure compilers, full after compilation is not precisely the criterion that we want. I think full after compilation is great for many other things when we talk about languages and expressiveness of languages, but not as compilers, of languages between each other. Then we want to use full after compilation to say that, you know, like for some work that we're doing with Domi is like, you know, iso-recursive types and eco-recursive types have the same expressive power. How do you do it? Well, you prove that there is a fully abstract translation between the two languages. Or the work that we're going to see in the afternoon session about securely interruptible enclaves. But because those are results that talk about the languages and not about the compiler. But if your result is about the compiler, I think you really want secure compilation, robust compilation in the sense of diagrams or robust state compilation. Kill me now, I guess. Right, so questions? Adobe.
This is more of a comment than a question. Some people seem to have the impression that people are saying abstract compilation is the best thing ever existed and everything else is bad. That's not at all at least what I am saying, and I think I haven't heard anyone say something like that.
No.
One comment here is that your analogy suggests that this universal compilation corresponds to sort of the existence of a background region, which is maybe broader than robust hyperproperty preservation, where you always need these traces. I don't really see the traces here. It's more about the existence of a background region, right?
But the back translation is a back translation that produces the same traces.
Oh no, that produces the same behavior for any definition of what behavior is.
Oh yeah, okay.
Yeah.
So yeah, interesting. I need to think more about this.
Just to mention some more related work, there's a conversation on constructed cryptography in Cryptol and Isabel library. And there they also focus on, so it's sort of similar to the ITM interaction we've seen before. And there they also focus on trace equivalence instead of by similarity. That sort of seems in line with what you're thinking about.
But then they do UC proofs? Or?
They do constructive crypto, which is a more abstract version
Oh, okay.
of UC. So they're related ideas.
All right.
And there was other related one to mention.
So how will you deal with probabilities?
Well, the if and only if in RHC, I mean, we can define RHC probabilistically, right? So basically, if we have some target trace then that can be generated, then with enough confidence, the probability of the generation of the source trace, we can generate analogous trace from the source context. So we can break the if and only if of RHC to be probabilistic, right? To account not for strict equality, but if we consider the total amount of traces, then there's a negligible amount of context and of interactions that generate the traces that are not equivalent. But for the vast majority of them, then yes, they are equivalent. I would think, well, that's off the top of my head. There might be some more precise ways to account for probabilities.
We well, we've run out of time for this session. Yeah, Tom, sorry. Let us thank Mark again.